Welcome back. So this is lecture 13 and we were talking about the likelihood function. Okay. So what I said in the previous lecture was that if you have a random variable x which is assumed to come from a probability density function f of x theta, right? This is the underlying probability density function. Okay. Then you can draw actually two kind of graphs. One is the graph of probability density function, which is the graph between values of the random variable x and this probability densities f of x theta. But you can draw this assuming theta is known and fixed. So some point fixed value of theta, okay? Fixed and known. So when theta is fixed and known, you can draw a graph between values of the random variable and the probability density function. Okay. This is actually can also be called the graph of your assumptions. So you're representing your assumptions about the random variable using this graph under some known value of theta, right? But once x is known, when actually x is known, at what point we can say that the value of the random variable is known? When we have collected some data. So when we have collected some data, then the value of the random variable would have some value. Okay, so one value or two, three values, it depends on the experiment. Then the value of the random variable is known in that case, right? So in that case, you can draw the graph between theta and these probability densities, because x here is known, theta is variable. In this case, theta was known, right? And x was the variable. In this case, theta is the variable. Now you can draw a graph between theta and f of x theta, right? So when x is known from the experiment, so when data is known. So after collecting the data, you can always draw the graph between theta and probability densities under your assumption, right? This is called the likelihood function, the second graph. This is called the likelihood function, okay? So this is actually telling you which values of theta are more likely to generate this data, which values of theta are less likely to generate this data. All right, so this is a brief wrap up of what we have covered. Okay, so let us take an example. Let us say you are doing a coin toss experiment. Okay, a simple coin toss experiment. What you are doing in this experiment, you are tossing a coin 10 times. Okay, you are tossing the same coin 10 times. Okay, what will happen if you toss a coin 10 times? You might get, let's say, 7 heads or 5 heads or 6 heads or 4 heads, right? And let's say that's the variable we are interested in, that how many heads you will get if you toss a coin 10 times. Okay, so this is the experiment you are planning. So what will be your assumptions? Okay, you need to make some assumptions about the outcome of this experiment. What is the outcome of this experiment? Number of heads. Okay, what could be the possible number of heads, possible value for this outcome? Anything between 0 to 10, right? So you need to make some assumptions that what is the underlying generative process behind this outcome. So basically number of heads that you will obtain in this experiment, right? So what is the underlying generative process behind this? So you have studied binomial distribution. So you can assume that the number of heads observed in this experiment can be assumed to come from a binomial distribution with underlying probability of producing a head theta. This is your assumption, that the number of heads observed in a 10 times coin toss experiment would come from a binomial distribution with underlying probability of heads being theta. You can also write the sample size being 10 here because they are 10 coin tosses, right? So this will determine how many heads you will get, right? So this is your assumption. Okay, Can you draw a graph of this assumption? Can you draw a graph of probability mass function? In this case, binomial distribution would have a probability mass function. Can you draw a graph of probability mass function here? What would that mean? Can you draw a graph between possible number of heads that you will see in an experiment and probability of obtaining that number of heads? Now, actually, the probability of a particular number of heads will depend on the underlying probability of producing a heads, right? So, basically theta needs to be known, theta needs to be fixed, only then we can calculate this. So, let us say hypothetically you assume that theta is 0.5. Okay. If coin is not fair, this probability could be anything else, but let us say for now we assume that theta is 0.5. Once theta is known and fixed, now you can draw the graph between number of heads and probability from binomial distribution, right? So, what would it mean is that because you are tossing the coin 10 times, then the probability of obtaining 5 heads will be highest, let us say here. Probability of obtaining 4 heads would be slightly lower. Probability of obtaining 6 heads would be slightly lower. Why the probability of 5 heads is highest? Because the underlying probability is 0.5, that is why. Probability of obtaining 7 heads would be lower, probability of obtaining 8 heads would be lower, and so on. Okay. So, this is the graph of probability mass function. I am not joining these points, you shouldn't, because this is a probability mass function, not density function. Okay. So, this is the graph of probability mass function. Right. So, up to this point we have not actually observed any data, right, we are just drawing a graph of your assumptions, right. So, whatever you have assumed. Now, let us say you actually performed this experiment and you observed this data. You observed that the number of heads when you toss the coin 10 times comes out to be 7. So, let us say this is your observation, the number of heads comes out to be 7. Basically, this is the value of your random variable now. Now, once this data is known, you can draw a graph between theta and probability density or likelihood. How likely is a particular value of theta to generate this data, number of heads equal to 7, assuming that number of heads comes from binomial distribution with underlying probability of heads being theta. Okay. How would I do this? What could be possible values of theta? Between 0 and 1, right. So, theta could be anywhere between 0 and 1 because this is the underlying probability of heads in a particular trial. Okay. Now, data is known, which is 7. So, you are obtaining 7 heads out of total 10 coin tosses, right. Now, if you plug in different values of theta, so you let us say take thousands of values of theta between 0 and 1, if you plug in all these values in a binomial PMF, given that x is 7, so value of random variable is 7, n is 10, okay, then you will have a function with respect to theta, right. So, what is PMF of binomial distribution, by the way? N chooses x, theta to the power x, 1 minus theta to the power n minus x, right. When n is known, n is 10 and x is 7, right. When x and n are known, then this function becomes purely a function of theta, right. However, theta does not have discrete values anymore, right. Theta has continuous values. So, theta could be any point value between 0 and 1, right. It could be anything, let us say 0.5554 as well, right. So, theta could be anywhere between 0 and 1. Okay. So, now you can draw a graph between this and different values of theta between 0 and 1, and this graph would come out to be like this, right. What you would get actually is that a value of theta being 0.7 is actually the most likely value. The value of let us say around 0.5 is slightly less likely. Theta being 0.9 is even less likely. Theta being 0.1 is almost unlikely. So, you are getting likelihood for different values of theta. This is what the likelihood function is, right. So, this is a function between probability densities which comes from the same function, your probability density or probability mass function, right. So, this is the graph between the values of your function, right, f of x theta and theta when x is known, when x is fixed, right. So, in case of binomial distribution, when in this case, in this example, when the number of heads is known, when this data is known, you can draw a graph between different values of theta and corresponding probability density of observing 7 heads. Okay. So, this is the probability density of observing 7 heads when theta is 0.7. This is the probability density, you can also call it likelihood of observing 7 heads when value of theta is 0.9. In fact, likelihood is a better term to use here, right. So, for example, this is the likelihood of observing 7 heads when theta is 0.5, right. So, what this graph tells you is that some values of theta are more likely to generate 7 heads, some values of theta are less likely to generate 7 heads, right. That is why this is called a likelihood function. By the way, the area under the curve for a likelihood function is not necessarily equal to 1, because this is not a probability density function or probability mass function, right. This is not a proper probability distribution. Okay. This is just called a likelihood function. It does not necessarily need to have area under the curve being equal to 1. Okay. That is why I am calling all these points as likelihood. You can also write likelihood here. So, this is an example of a likelihood function you can draw. But the important point here is this: what this likelihood function telling you, why we are drawing this, why it is important. The reason is this, that after seeing the data, we are drawing a graph of how likely are each values of theta to generate this data. Okay. So, what we are essentially showing in this graph is that which values of theta are likely to generate this data. Okay. This is exactly what we want to do in parameter estimation. Okay. So, basically we are estimating the parameter here, that what value of theta might have generated this data. Okay. Now, in a likelihood function, you are not getting a single point value of theta, right. This graph does not tell you exactly which value of theta would have generated this data and number of heads equals to 7, but this is still giving you a lot of information. And what information is that? That which values of theta are more likely to generate this data, which values of theta are less likely to generate this data, right. This is giving you the whole likelihood function, that which values of theta are more likely, which values of theta are less likely, right. So, the advantage of using a likelihood function is this, that you are not losing any information, because there will always be a randomness because of your probability, because of your probability distribution and because of the data, because the sample of data you have collected, right, it is a limited sample. You do not know the whole population, you just have collected a sample from the population, right. So, it would always have some variability, right. So, this likelihood function takes care of that. Basically, it is giving you uncertainty in the parameter estimate. It is not telling you a point value of theta, it is telling you a whole distribution, that which values of theta are more likely, which values of theta are less likely, right. So, it contains the uncertainty around parameter estimate. Basically, it tells you that most likely the value of theta is somewhere between 0.5 and 0.9. Which is exactly what we want, right, in the Bayesian framework. We will see later on. So, this idea of uncertainty is extremely important in Bayesian inference, right. So, that is why we use the likelihood function. By the way, in frequentist framework, once you have the likelihood function, you can just get what value of theta is most likely, right. So, you can calculate the mode of this function, right, mode of this graph. What is the maximum value of this function? The maximum value of this function is at theta equals to 0.7, right. So, a value of theta at which you achieve maximum likelihood is called the maximum likelihood estimate of theta. Okay. And this is the point value you often get in your in frequentist inference, right? In frequentist inference, you get just a point value of your parameter, right? So, for example, when you are doing a linear regression, you will get a point value of estimate of alpha, beta, all those intercept and slope parameters, right? That point value is actually maximum likelihood estimate of theta, right? And that suffices in frequentist framework because we are interested in point values of theta. In Bayesian framework, we are not interested in point values, we are interested in whole distribution, right? And we will come to the reason why exactly, right? But one reason you can understand right here is this, that this parameter theta is not considered to be a fixed quantity. Parameter theta is considered to be a random variable which would have its own distribution. Okay. So, we are never interested in estimating a point value of theta because it's a random variable. So, what we are interested in? We are interested in estimating what is the underlying true distribution of this parameter theta. Not point value of theta, but the underlying true distribution. What underlying true distribution tells us? That which values of theta are most likely, which values of theta are less likely, and so on. It tells us a distribution of values of theta, right? So, this is a basic introduction to the likelihood function. Let us see how do we draw a likelihood function in R. Okay. So, we can draw this function in R as well. So, let us see. So, let us say you assume that you are doing this 10 coin toss experiment. Okay. X is a random variable which indicates number of heads in a 10 coin toss experiment, right? And you assume that X comes from a binomial distribution with underlying probability of success theta and sample size n equals to 10, right? This is our assumption. Let us first draw the graph of our assumption. Okay. So, let us first draw the probability mass function. In order to draw probability mass function, we saw that we need to fix the parameter theta because a probability mass function is a function of theta as well as x, right? And we need to draw a graph with respect to values of x. Okay. So, first we need to fix theta. So, let us say we fix theta at 0.5, okay, and let us draw the graph. If you fix theta at 0.5, then we want to draw a graph for different values of x. So, let us take different values of x. What values x can take? Number of heads? It can take any value between 0 and 10. Okay. So, let us basically calculate probabilities corresponding to each value of x, so which you can calculate using d binom function. This function calculates the value of the probability mass function. So, here you will pass on x, sample size is 10, and now the underlying probability of success is actually theta, which is 0.5 in this case, right. Now, if you draw the graph between x and probability, you will see the graph of probability mass function. See, so this is the graph of probability mass function. So, the value at the 5, the value of x being 5 is has the highest probability, and then probability decreases for these values, right. So, this is the graph of probability mass function under the assumption that theta is 0.5. Okay. How it would change if I assume theta is 0.6, not 0.5? This is how it would change. Now, the value with the highest probability is 6, and values around 5 and 7 are less probable, right. So, this graph would change under different assumptions about theta. So, this is your PMF. Let us draw the likelihood function. Okay. You can draw the likelihood function only after observing the data. PMF you can draw before observing any data. So, let us say the data you have observed is this. You observed that the number of heads in the experiment is 7. Okay, so this is what you have observed. Okay, so this is your data. This is a fixed quantity now, fixed and known. Now you can vary theta. Okay, so let us vary theta between 0 and 1. Okay, so let me take different values of theta between 0 and 1. Okay, so it's not discrete, could be any, so it's a continuous scale between 0 and 1. Let's say I choose 10,000 values of theta between 0 and 1. Okay, now for each value of theta I will calculate the likelihood, given that the data is x equals to 7. How do I do that? I can again use d binom function. Remember, the function remains the same. I'm using the same function f of x theta, right? It's just that in this case theta was fixed, in this case x is fixed, right? So I'm using the same function, right? Data would go here, so data is 7, x equals to 7, right? Sample size is 10, so that is also fixed, and here I would pass the vector of thetas. So underlying probability of a trial is this vector of theta. So I'm basically calculating it for different values of theta. Let me call it likelihood. So I will get a vector of likelihoods corresponding to each value of theta. Now I can plot a graph between theta and its corresponding likelihood. This is what I get. See, this is actually the graph of the likelihood function. Okay, this is the likelihood function. When you assume that your data comes from a binomial distribution with underlying probability of success theta, and you observe that the data is x equals to 7, then this is the likelihood function, which tells you that which values of theta are more likely to generate this data x equals to 7, which values of theta are less likely to generate this data. So for example, values less than 0.2 are almost unlikely to generate this data. Values near 0.7 are most likely to generate this data. Values around 0.4 are very, very less likely to generate this data, right? This is what the likelihood function tells you. Okay. All right. So there is one more interesting thing you will see here is this, that what happens if you increase the sample size. Okay. So rather than tossing the coin 10 times, let's say you toss the coin 100 times. Okay. So what happens when you increase the sample size? Okay. So let's say you toss the coin 100 times and you get 70 heads, right? So basically the underlying thing is same, right? So in this case you toss the coin 10 times and you obtained 7 heads. Here I toss the coin 100 times and let's say the data I get 70 heads. Okay, let us see how the likelihood look like. You can think that still the most likely value will be 0.7, because this is the number of heads you are getting and this is your total sample size, right? So it would be around 0.7. But let us see the overall likelihood function, how it looks like. It looks like this. See the difference compared to the previous plot? You can see still the most likely value is 0.7 and the values around 0.6 and 0.8 are less likely. Okay, but something had changed between this graph and this graph. What had changed? This graph is much narrow. The spread of this graph is much less compared to the previous one, right? The previous one told us that the likely values of theta are somewhere between 0.4 and 0.9, and this graph tells us that the likely values of theta are between 0.6 and 0.8 strictly. Why? Because the uncertainty has reduced, because we have a larger sample size now, just because of that. Okay, nothing else has changed, it's just that you have a larger sample size. You have tossed the coin 100 times rather than tossing it for 10 times. Just because of increased sample size, information in the data increases, and that's why you get a narrower spread. So basically the information here increases. So likelihood actually tells you something about the data, right? You're drawing the likelihood based on some fixed data, right? So likelihood gives you whatever is the information there in the data, right? So if data contains more information, the likelihood will be more informative. So you will have less uncertainty in the likelihood, right? When the data was small, you had more uncertainty. When data is high, you have high uncertainty. You have less uncertainty, right? And that's a very important point when we further go on in doing a statistical inference. Point is this, that when you have more data, it reduces uncertainty in parameter estimation. When you have less data, you will always have a lot of uncertainty in parameter estimation, right? So if you want to do reliable statistical inference, you should have larger sample size. All right. Now coming back to the likelihood function here, right? So I showed this example for a binomial distribution, right? So in a binomial, you assume that x, let's say number of heads, has a binomial distribution with underlying probability of success theta, right? What it means is that the f of x theta, the underlying probability mass function, is n chooses x, theta to the power x, 1 minus theta to the power n minus x. Okay, fine. Now let us say that this you have collected some data, okay, and your data is this, that x comes out to be, let's say, x naught. So this is your data. Okay. So after collecting the data, the value of random variable x is known, which is x equals to x naught, right? Once the data is known, you can draw a graph of probability, you can draw a graph of likelihood function, which is f of theta, right? Because x is known. Let me write it like this. X is known to be x naught, and now it just remains a function of theta. So you can write it like this: n chooses x naught, theta to the power x naught, 1 minus theta to the power n minus x naught. Fine. So this is your likelihood function. Let me write it clearly here. So my likelihood function is n chooses x naught, theta to the power x naught, 1 minus theta to the power n minus x naught. Now this just remains a function of theta, because n and x naught are known. N and x naught are known and fixed. So basically your data and the sample size are known and fixed. Okay. Now suppose I want to calculate maximum likelihood estimate of theta. This is the likelihood function of theta. I want to calculate maximum likelihood estimate of theta. What does that mean? At what value of theta, the function achieves maximum value. At what value of theta the function achieves the maximum value. Basically, it is the value of theta which has highest likelihood. So what value of theta has the highest likelihood of generating this data? Okay. How do I calculate this? Well, I just need to calculate maxima of this function. How do I calculate maxima of any function? I can equate the first order derivative of f of theta with respect to theta equals to 0. So value of theta at which function achieves its maximum should satisfy this. So the derivative of this function with respect to theta equals to 0. Let us calculate the derivative of this function with respect to theta. So the function is n chooses x naught, theta to the power x naught, 1 minus theta to the power n minus x naught, right? And we are differentiating it with respect to theta, and you're saying this should be equal to 0, right? So this can be taken out because this does not have any theta component. So only thing we are concerned about this quantity and this quantity, which has theta component, right? So in doing differentiation, we would have it something like this. So we are differentiating this term, right? So you can basically, these are two functions multiplied with each other. So you can apply this formula that you take out this quantity outside the differentiation and then differentiate just 1 minus theta n minus x naught plus take out this quantity outside differentiation and then this differentiate theta to the power x naught, and this is equals to 0. Okay. What would happen if you differentiate this? So, theta x naught, when you differentiate this, this would become 1 minus theta to the power n minus x naught minus 1 into n minus x naught, right, and then differentiate 1 minus theta as well. So, that would become minus 1. Okay, so, this is the first quantity. The second quantity will be this one, 1 minus theta to the power n minus x naught, and you differentiate this, then x naught into theta to the power x naught minus 1, okay, equals to 0. Okay. So, actually you can take out these common quantities. So, in this case you can write it like this. So, theta x naught minus 1. So, I am taking out whatever is common in both these quantities, theta x naught minus 1 into 1 minus theta n minus x naught minus 1, and what would be left inside will be theta into n minus x naught into minus 1 plus 1 minus theta into x naught, and this is equals to 0. Okay. So, either this equals to 0 or this equals to 0, right. So, let us focus on this quantity. So, this would be 1 minus theta into x naught minus theta into n minus x naught, and this is equals to 0. Okay, let us solve this. Now, this is x naught minus theta x naught minus n theta plus theta x naught equals to 0. Okay, this will go. What we have is this, x naught minus n theta equals to 0. That means theta equals to x naught by n. This is the maximum likelihood estimate of theta. So, at this value of theta, the function would achieve its maximum value, right. This is it. So, you can call it, this is the maximum likelihood estimate of theta when you assume that x naught, the random variable, comes from a binomial distribution, right, and x naught is the observed data and n is the sample size. All right. So, this is it on the likelihood function. In the next lecture, we will start some basic foundation of Bayes theorem. So, basically we will go back into those probability axioms and figure out the basic foundation of the Bayes theorem. All right. Thank you very much.